Right now, all around you there are invisible signals. They're carrying our voices, our videos, our data, flying across cities, and even through deep space. But here's the thing. These signals don't start out with any meaning. They begin as just pure, empty energy, a silent wave, just waiting for a message. And this is the story of how we teach that energy to speak.
I mean, have you ever really stopped to think about it? What does that Wi-Fi signal beaming through your house actually look like? It's not just some magic cloud of internet. No, it's a physical wave, one that has been sculpted and shaped with some absolutely incredible ingenuity.
You know, it all starts with this: a pure, perfect, clean carrier wave. Just think of it like a single, continuous note being held on a synthesizer. It's predictable, it's steady, but it's carrying exactly zero information. So the fundamental challenge for all of modern communication is, how do we take our ones and zeros, the language of computers, and embed them onto this simple, featureless wave?
So how do we do it? Well, the answer is a process called digital modulation. And really all modulation is the art of changing or, well, modulating the properties of that carrier wave to represent our data. It's how we give our bits a physical voice so they can actually travel through the air to get where they're going.
Okay, so to teach this wave how to speak, we first have to understand its language. What are the basic things about a wave that we can even change? Well, it turns out there are three main ways we can get it to talk.
So every single wave has an amplitude. That's basically its height or its power. It has a frequency, which is how fast it's wiggling back and forth, and it has a phase, which is a little trickier, but you can think of it like its starting point or its rhythm. And by controlling just these three things, we can encode pretty much any data we can dream of.
All right, let's start with the simplest tools in the toolbox. With something called amplitude shift keying, or ASK, we just change the wave's height. A big, tall wave could be a 1, and a short little wave could be a 0. Simple as that. Or we could use frequency shift keying, FSK. Here, we change its speed. A fast wave is a 1, a slower wave is a 0. Pretty straightforward, right?
But that third language, phase, this is where things get really, really powerful. Instead of just tinkering with the height or the speed, we can actually shift the wave's internal rhythm. We can tell it to start its cycle from a different point. This method, phase shift keying, it just unlocks a much more sophisticated way to send our data.
And this is where we need to take a big leap. Seriously, we're going to stop looking at these squiggly lines over time, and we're going to start looking at our data in a completely new dimension. This is the moment where those simple waves transform into these beautiful, complex constellations of pure information.
Okay, so we've got to rewire our brains for a second here. What we've done is we've taken that one-dimensional wave and we've represented it in a totally new way. This is called a signal space diagram. Instead of a wiggly line, every possible state of our signal, every piece of data, is now a single, distinct point of light.
But you can see the problem, right? A single line is, well, it's limiting. To get the insane speeds we need for streaming 4K video or gaming online, we have to pack way more information into every signal we send. We've got to break free from that one-dimensional line and expand into a whole new dimension.
And this is how we do it. On the left, if you only use phase to encode data, all your points end up in a circle. That's phase shift keying, or PSK. But if you get clever and use both amplitude and phase at the same time, you can create a perfect grid of data points, just like you see on the right. This is quadrature amplitude modulation, QAM for short, and it is the absolute workhorse of modern Wi-Fi and 5G.
I mean, just look at how powerful this is. In this 16 QAM constellation, every single one of those 16 stars represents a unique group of 4 bits, like 1011 or 0010. So by sending just one of these points, what we call a symbol, we've actually transmitted 4 bits of data all at once. So the math is simple. More points in our constellation means more bits per symbol, and that means a faster connection for you.
But this elegant, perfect little universe of data is not a peaceful place. As our signal travels from a cell tower to your phone, it faces a constant, relentless enemy. Every single signal has a battle to fight, and that enemy is noise. Think of it as random electrical energy that just gets smeared all over our perfect signal, and it comes from everywhere. Other electronics, radiation from space, even the heat from the atoms in the air. It is the inescapable static of the universe, and its only job is to distort our carefully crafted message.
So what does noise actually do to our beautiful constellation? Well, a clean signal has these perfect fixed points of light. Your phone knows exactly where each star is supposed to be. But when noise hits, those points aren't fixed anymore. They start to jitter and waver. They become these fuzzy clouds of probability. And now the receiver isn't so sure where the original point actually was.
Now, here's the really crucial thing to get about noise. It doesn't just teleport a signal point to some random spot. It just nudges it around its original position. And what that means is that the most common errors happen when noise pushes a point just far enough that the receiver confuses it for one of its immediate neighbors. This makes the distance between the points the single most important factor for having a reliable connection.
And that right there, that brings us to the very heart of this whole story. The central conflict in all of digital communication. It is the constant, eternal battle between our desire for more and more speed and the harsh physical reality of a noisy world.
And here's exactly how that trade-off plays out. With 4QAM, we're sending 2 bits of data with each symbol. The points are really far apart, so it's incredibly robust and reliable, but it's slow. To go faster, we jump to 16QAM. Now we're sending 4 bits at a time, twice as fast. But look how much closer those points are. We've just sacrificed reliability for speed. And if we push it even further, to 64QAM, we get 6 bits per symbol, but now that constellation is dangerously crowded.
This table just lays it all out, plain and simple. As you crank up the modulation, going from QPSK up to 64QAM, the bits you can send per symbol goes up. Awesome, that's speed. But at the same time, the noise resistance plummets, which means the chance of an error goes way, way up.
Now, we're not talking about a small difference here. It is dramatic. Under the exact same conditions, just going from an 8-point constellation to a 16-point one can increase the probability of an error by over 1,000 times. Packing those stars closer together has a massive, massive cost.
So this is it. This is the moment of failure. You have a single point representing a specific chunk of data. It gets hit by a random burst of noise. It drifts just a little too far, and it crosses this invisible line, what engineers call a decision boundary, that separates it from its neighbor. Your phone's receiver sees it on the wrong side of the line, and it makes a mistake. A 1 becomes a 0, and your data is corrupted.
And look, this isn't just some theory in a textbook. This delicate dance is happening billions of times a second right now inside all of your devices. Your Wi-Fi router is constantly measuring the noise in the room and deciding, okay, can I use a fast but fragile 64QAM right now? Or is it too noisy and I need to drop back to a slower, more reliable 16QAM? This is exactly why your video starts to buffer when you walk to the other side of the house. Your router is choosing reliability over speed just to keep the connection from dying completely.
So really, everything we've talked about, it all boils down to this one constant, dynamic balancing act. The entire field of modern telecommunications is built on this one fundamental trade-off: our seemingly infinite demand for more speed versus the very finite, very noisy reality of the physical universe. And it leaves us with a pretty fascinating question for the future, doesn't it? We are always pushing, always inventing new ways to create denser and more complex constellations to feed our hunger for data. But as we do, we have to ask ourselves, in our quest for infinite data from a finite world, what happens when we finally run out of space between the stars?